Well, hi, everybody. This is a recorded Zoom chat with Jeff Tepper. You remember Jeff from a couple of weeks ago. We did a live stream with Jeff Tepper, University of Puget Sound, and Rich Gashnig, University of Massachusetts Lowell. But now we have Jeff all to ourselves. Jeff, how are you today?
I'm great. Thanks, Nick.
Thank you for being with us. And thank you, Jeff, for watching these live streams in this Idaho Geology Miniseries that we've been doing. I asked you to come back on because maybe you'd have some reaction to some of the shows. So, viewers, if you haven't been keeping track, we had Jeff and Rich Gashnig on together thinking about the Idaho batholith. Then we had Gene Humphreys talking about the Idaho slab curtain. He was a seismic tomographer. Then we had Basil Tikoff, University of Wisconsin, who was not a big fan of the Idaho slab curtain and was emphasizing the role of the Lewis and Clark line and a major switch at the beginning of the Chalice Magmas, motion on that Lewis and Clark line. And then most recently, just a few days ago, Spencer Fuston from University of Houston, who was also a tomographer but had some slightly different stories to tell. But we're back to Jeff, and it's Jeff Tepper's model involving the Chalice magmas and the rollback of the Farallon plate that I want to keep building around and with. So, Jeff, maybe opening comments, if you would. Did you like some things you heard from those guests? Were there some things that you were kind of thrown by and surprised by? Before we go to a couple of slides, what's your general reaction to what you've been hearing?
Well, it's been great. So, as I said before, other people have said that you're a clearinghouse where we get to hear other people's views that we probably should have read their papers, but we haven't always kept up.
Right.
So, as I told you, I've listened to Basil twice, and I've listened to Gene twice, and I was live with Spencer. So it's incredibly helpful to hear other people's areas of expertise and think about how they fit in. And so I would say mostly I like what I heard, and I have questions about some things that um, I'm not sure how they whether they support or contradict my story.
Yeah.
But
Yeah.
overall, I've been very pleased to hear, that the bigger picture.
Well, let me try to paraphrase verbally in 2 minutes or less your model, and then you can correct me, and then we can go to a couple of
Okay.
slides that
All
kind of
right.
are what you're hoping to show us as you kind of have some new thoughts. So, if you're new to us, viewers, this is Jeff Tepper, who has a model to explain a northeast to southwest age progression of igneous rocks, both plutonic and volcanic igneous rocks in Washington, 52 million years ago in extreme northeastern Washington. And then as we work our way to the southwest across the state of Washington, we get younger and younger, a 52 to 44 million year old age sweep. And there's a strange uh, line of 48 to 49 million year old lavas that appear to be kind of a northwest southeast trend through the Cascades that Jeff is interpreting as a major break to the Farallon plate that is rolling back or drooping in the subsurface beneath Washington. Would you care to correct or add to that verbal
No, that
summarization of your model?
that's good.
Okay. What I was asking then is, since I love that model of Jeff's, can we go east into Idaho and even further east to see an earlier set of signatures with the rollback, or at least where does this story start with these Chalice magmas? Maybe that's where we go to you, Jeff. I don't know if you want to share a screen or if you just want to just generally get us
Um,
into it, like what intrigues you about to the east of Washington.
okay, so I'm going to start off with a disclaimer that I have worked in Washington and just barely across the border into Idaho. So I am
Yes.
not an expert on the geology of other areas, but early on, when I recognized this magmatic age progression in Washington, the logical question was, does it occur farther east? And I knew about rocks in Montana, for example, that have some subduction traits. They're not normal subduction related rocks, but they have some characteristics of a subduction involvement in one way. So I thought, let's look at the ages of these and see if we just extrapolate the story back. And the very fast answer was no.
Okay.
So I, I, I do not think that the age progression that we see in Washington extends very far beyond the boundaries of the state. I also don't think that precludes a role for the Farallon plate in activity farther east. So we know the Farallon plate was subducting for a long period of time, and Spencer's tomography shows that portions of it are, as far east as Georgia. So there's a lot of subducted Farallon plate under North America. And I think in order to have rollback in Washington, this little piece in Washington has to disconnect from that.
Yes.
And I like the story that that disconnection is what led to the slab, the hanging slab or the curtain under Idaho that Gene has imaged. I'm not a tomographer, but I don't really necessarily understand why all pieces of a foundering plate have to do the same thing. So my hypothesis was that in Washington there's a systematic rollback,
Right.
but in other places the slab may have just foundered, and you don't get a systematic age progression, but you could get some magmatism associated with that. It just wouldn't look like arc magmatism. So this is where I could share with screen and show you
Let's do it.
some magmatism that I has been associated with the Farallon slab, but way farther to the east and doesn't look like the stuff we see in a normal subduction zone. Okay.
I love it. I love it.
All right, let's see if I can do this.
And then after we look at a few of these slides, then we'll go back and forth a little bit. Great.
Let me see.
Full
I
screen?
want to, is it not full screen?
It is. Yep.
Okay, and I want to go
Yep.
back one slide.
Okay.
Actually, I'll go back two. So
Great.
um, it's difficult sometimes, especially if I'm just using my hand to convey the rollback story. So a friend of mine here in Tacoma, Ken, sent me an article that has this figure in it, which is a nice illustration of the idea of some of the phenomena that go with rollback, even though this particular diagram is not drawn to represent Washington State.
Mm-hmm. Mm-hmm.
But what is similar, so here's the Farallon plate, it's rolling back. As it rolls back, then we have a hot mantle, which we call a asthenosphere, come welling up. And that upwelling mantle then is a heat source, which affects the crust in several ways. So one is it drives melting of the crust. And because we are melting old arc rocks, we are making what look like new arc rocks, the chalice. So one of the mysteries of the chalice early on was that this looks like an arc. They have hornblende. They're the kind of characteristics, that Basil was talking about that would say this is an arc. But you can get those characteristics by essentially recycling arc material.
Mm-hmm.
And so these little red pods here represent melting that's driven by uh, upwelling hot mantle. And then you're also, because you're thermally heating and expanding the crust, you can have uplift. And we mentioned this briefly in one of the previous live streams, I think. And then as the slab rolls back, then both of these features, the melting and the uplift, migrate in the direction that the rollback is occurring. So in the case of the chalice, this is rolling northeast to southwest across Washington. This zone of volcanic centers is migrating, and then this topographic it's a more subtle effect, and we don't really see in modern geology the evidence of that. It's much more subtle, but it comes in the form of changing drainage patterns and things like that, which you can see in the sedimentary record if you look closely.
In Washington, Jeff, do you think between 52 and 44 that migrating bulge was a thing?
I do. There's a paper, I believe by Smith, that documents this. And then most of that work was done a little farther south. So it's the contours of this bulge sort of end as you're getting into Washington. So it's not their study didn't extend as far north as Washington, but the process would be the same. So I think if there were exposures, then yes, we would probably see evidence of the same kind of thing.
Oh, yeah. Yeah. A lot of it's under the CRBs. Got it. Okay.
Right.
All right. Great.
Okay.
Please.
So that sort of catch up. So this is the new figure that I wanted to share. So I just have two slides. So this is from
Okay.
a 2014 paper by Duke et al.
Mm-hmm.
And what they were looking at is some really unusual igneous activity that defines a belt from Arkansas across the Great Plains and ultimately up here into western Montana and Idaho.
Mm.
So these are some rocks. Some of these rocks are called kimberlites and carbonatites. Kimberlites are the rocks that bring diamonds to the surface. So
Mm-hmm.
there are diamond deposits in Arkansas that are a tourist attraction, and this is why they're there. And carbonatites are another very uncommon igneous rock. They're actually a magma made of molten calcite, which is not normally an igneous mineral. Both of these are magmas that come from incredibly deep in the deep in the mantle. So I think I would use as a sort of guiding principle that when you have magmatism, there's been some disturbance of the mantle. So magmas don't just suddenly occur out of thin mantle. There's something that triggers melting. And this paper identifies that this northwest trending belt seems to align with F1, which is the tomography image of a piece of the Farallon slab. So they're suggesting that somehow the edge of the Farallon slab at great depth in the mountain, something like 400 kilometers down,
Huh.
is triggering melting. So I think I'll go to the next slide, which is a couple of cross sections that show what they think is going on at different snapshots in time. But the common theme to these is that you're seeing melting in the mantle at a variety of depths, but generally fairly deep, triggered by some uh, coming apart of the Farallon plate, but
Okay.
coming apart much farther east and much deeper than what we've been talking about in Washington and Idaho.
Mm-hmm.
Okay, so here are three snapshots in time. All of them are cross sections from west to east. And the depths here, I don't know if you can read these, but they're kind of small. But the bottom down here, where you see mantle transition zone, that's about 400 kilometers below the surface.
Mm-hmm.
And so the earliest one here, about 83 to 75 million years ago, um, that one I'm not going to promote too much. They've got something going on under the Idaho batholith, which we've already established is not is a crustal melting phenomenon, and there could be some heat input from below that was assisting in the melting. But I
Mm-hmm.
think the more interesting ones are this farther east stuff. So this is some of these unusual volcanic rocks in Montana and here at Black Hills of South Dakota. And their hypothesis is that the brown here would be the Farallon slab, that it has subducted to down to the mantle transition zone. And I remember that Spencer is able to see the Farallon slab sort of scooting along here at the mantle transition zone. And he sees it as being a fairly intact, continuous slab. And I don't know how to, I can't criticize that, but my question to him was, can you distinguish whether it's a broken up slab or a continuous one? And he said it's probably continuous. In
Mm-hmm.
this paper by Duke, it's a more broken up
Mm-hmm.
feature, and I don't know if that's important or not. But the idea is that the Farallon slab is indirectly responsible for disrupting the mantle and causing magmatism much farther east. It just doesn't look like normal subduction magmatism because we're melting at much greater depth and we're not melting by the normal adding of fluids that takes place in a, like the modern Cascade Arc.
Hmm.
And in the final snapshot here, this is now the sort of time frame that we've been thinking about, and they are proposing that the chalice are a shallower manifestation of the same process.
Huh.
So my question, I guess, would be, um, is there any reason why the effects of the Farallon slab farther east um, could look like this?
Because you need your first break someplace.
So I think, yes, we need for the rollback in Washington story, we need a break probably somewhere around 60 million years ago
Yeah,
and somewhere under western Montana, probably if you just want to take the length of material that's represented by Gene's curtain and
yeah.
attach that to the intact part of the Cascadia slab, we're probably somewhere in western Montana. But it was a huge slab, and it had transform faults and other kinds of planes of weakness in it. Um, we know some of the factors that lead to flat slab subduction. So that's been one of the topics where there's been disagreement, or at least different interpretations of the data. And I I personally kind of like the flat slab for a couple of reasons. One being that there wasn't any arc magmatism in Washington immediately preceding the chalice,
Yeah.
yet there seems to have to have been a slab there because subduction was ongoing. And we know that two of the factors that favor a flat slab are a high rate of subduction and an old subduction zone, a high rate of subduction, and a very large slab.
Hmm.
And all three of those are met
Hmm.
with the Farallon plate in Washington. So I know that I totally agree with, Basil pointed out that the rocks that some of the rocks that look like they're relaxation granites have nothing to do with subduction. I completely agree with that.
Huh.
My question would be, does that preclude there having been a slab under there, even though the slab was not directly responsible for the relaxation?
Right. Hey, would you mind stopping your share for a
Yep.
sec? So
Okay.
this is great. You're right in the zone here. Let's just keep going for a few more minutes. This doesn't have to be a 2 hour thing.
Okay.
Um, did it surprise you that Spencer kind of resisted the idea that he was a flat slab guy? Did you know that he was visualizing a slab so deep as opposed to at the base of the continental crust?
It did surprise me that he was uh, not a flat slab proponent. Um, I don't know how you know what angle the Farallon slab had between the time it was subducted and the time it wound up at the transition zone 400 kilometers down.
Mm.
So
Mm.
it certainly makes sense that once it reaches that barrier, it's going to be traveling flat. I just don't know how you know that it wasn't flat farther inboard, at least than Idaho, before it steepened and wound up at the transition zone.
Mm. You're a Washington guy. You've said that a few times off camera and now as we're
Right.
recording this thing, and I totally get that. Do you have any sense of the geochemistry of these chalice magmas east of Washington? And what kind of chemistry are you looking for to have it fit into this disturbed Farallon story that far east?
So I probably would say that I don't want to call anything that is farther east a part of the Chalice story because I feel like that has a
Oh,
geographic
okay.
constraint to it. So we'll
Yeah.
call them, Eocene magmatism or something like that. But I don't know that I want to broad. I don't think we should change the definition of the chalice.
Okay, good.
I don't think there's a chemical fingerprint, and I don't
Okay.
think we need one because a chemical fingerprint is a combination of two things: what's melting and what's the process that's causing the melting. And in the case of these much farther east rocks, we're not melting the same thing that we were melting in Washington. So we wouldn't
Right.
we're melting mantle and we're melting it much deeper in the stuff I looked at in Washington, we're melting the crust. So there's a very and the Idaho batholith is melting of crust. So there's a profound difference in what you would expect and therefore in what we see between Eocene rocks in Washington and Eocene rocks in Montana. The Montana stuff is coming from much deeper. It's coming from the mantle and it's coming from deep in the mantle. And how deep it comes from in the mantle affects its composition. So we
Plus,
talk
it's
about,
co-
I was going to
plus
say, what,
it's coming up through the craton versus the secretive
right,
terrain stuff. Isn't
right.
that a
And
significant difference?
and so if it's interacting on the way to the surface, then that makes the difference. I think in at least in a lot of this, and again, I don't work in Montana, so
Right.
I could be corrected by somebody, but it seems like a lot of this, especially the more basaltic stuff, is coming through the crust without acquiring a lot of crustal signature.
Hmm.
And what signature it gets is probably fairly subtle. So it's not changing a basalt into an andesite. It's a much more subtle sort of uh, seasoning.
A few more. I mean, I think where I want to go next is some of these plate snapshots out in the Pacific. And I know you don't want to go to the other side of the Pacific and start talking about that
Right.
stuff.
I don't know anything about that. I mean, that's
Right.
outside my pay grade. So
But in general, I'm not going to push you in that direction, I promise. But in general, it was a revelation to me. Was it to you that potentially there are much larger forces to create a major change 55 or 53 million years ago? In Basil's case, he's saying this is a global reorganization to then have this major extensional story. Does it seem to you also like this might be we're trying to look for your 60 million year old break and we're trying to look for a few other things just within the frame of Western North America when it might need to pull out on a more global scale to have some answers maybe to what we're seeing locally?
that was not the first time that I heard that what's happening in Washington and the Eocene is one segment of a much bigger story, and I
Mm,
completely buy that. Um, I think there's actually things happening in the Atlantic at the same time. I'm not sure exactly what the age of opening of the northernmost part of the Atlantic is and the magmatism in Greenland,
mm,
but I think those are sort of in the same ballpark time-wise. I think, for someone to figure out the big picture, there's going to be people like me who look at little places and figure out those places, or at least come up with a story for those places. And then there's going to be other people that come along and say, here's all these places that have been studied in detail. How do
uh,
they fit together? So
uh.
I'm not I'm not one of those fit together the whole story people, but I
Well,
think
maybe,
there is a story there.
yeah, well, maybe I do bug Karin Siglock then and Mitch Mahalanuk, who do appear to be dealing with much larger storylines and more tomography and trying to marry the tomography, Karin, with the surface stuff in British Columbia, at least, Mitch. I don't know, maybe I need to go there because it is starting to feel not only is Basil and others pulling me older than I thought that I would go, but now maybe I'm being pulled wider than I thought I was needing to go for some of these things.
Well, you're the captain, but I could see that this is this is going to grow into something very large. And
All right.
I think there
Yeah.
are, it's not entirely, I think not entirely a tomography story. There's a surface geology story, a tectonics story, and that will be just as important as the tomography, if not more so, because I think there's a lot more,
Hmm.
paleomagnetism and
Right.
geochronology that are placing constraints on where things were and when they changed.
Hmm. Thank you. Let's finish this up by seeing if I can share my screen, and I'm going to show you a couple things that are going to look familiar. Can you see this?
Yes.
Okay. Um, I think one of the main things that I learned from Spencer, maybe I was cornering him and pushing him to say it, but I think I heard from him that he's comfortable with resurrection Farallon
Right.
as this boundary. Are you
Right.
all the way there too now?
I am. So this is a fairly, this I think is from a poster that I did with Ken Clark at AGU or GSA quite a while ago. So I would replace Kula with Resurrection.
Interesting. Okay, yeah, this is for sure 2019 at that section meeting of the GSA in Portland where I first caught wind of this with you standing in front of your poster. Maybe it went earlier than that, but this is where I caught wind of it. So this is your poster with Ken. Now we're just freelancing. I've ignored the Clarno completely. Why did you include the Clarno Formation in Oregon in this poster?
Well, the Clarno is a very enigmatic unit, and I haven't worked on the Clarno, so I'm not going to say a lot about it, but um, it
Mr.
falls in.
Disclaimer. Go ahead.
Well,
Go ahead.
I don't know what you're going to ask me next, so I have to be careful.
Go ahead. Yeah, why did you have
It,
so it's
but
a strange unit and
it's a
it's time.
strange unit. It's kind of before the Cascades, but it has some arc-like traits.
Okay.
So when we put this diagram together, I thought, oh, look at that. There's the Clarno sitting right on top of this slab window that we were drawing. So
Hmm.
that's the only unit I put on because it is a well-known unit in Oregon and it's not well understood. So I just thought this is a something to put on the poster and see if somebody comes by and asks questions or has ideas about it.
Sure, sure. Um, so I'm really putting you on the spot now, but why not? You know the spirit of this. So this is 52 million years ago. You did
Right.
this 2019. Besides changing this plate name to Resurrection, are you happy with this offset that you and Ken drew?
I don't think we feel we need that anymore. We wanted the offset so that Siletzia would be symmetric about a spreading ridge, because there
Hmm.
was some evidence early on that ages got older as you went from the center to the outside or
Okay.
to the north and south. And I think that geochronology has been called into question because there wasn't very good stratigraphic control. So it
Mm.
wasn't clear that the ages represented the onset of volcanism in different places. So we put that in order to allow for that age story to be intact. And I believe Iceland does look kind of like this. The inset map on the bottom there shows the spreading ridge, but then the spreading ridge, the Mid-Atlantic ridge, is offset to the east
Hmm.
in Iceland. So it's not without precedent to have
Yeah.
a hotspot impinging upon a ridge and the ridge to be offset. But I don't think we need that.
Okay. Let's do the other two. So there's our slab curtain. Gene Humphreys, a few live streams ago, viewers reminding you, and now we've accreted Siletzia by 49. Again, we're still thinking maybe resurrection. Anything else you've evolved in thinking from this window here, Jeff?
The details of the lines have changed a little bit, but it's basically the same. So
Okay.
the blue line there that represents the northern edge of the Farallon plate is moving northward, and it's as it moves northward, the subduction zone indicated by the hatchers on the
Hmm.
plate boundary there, that's migrating northward. So you're converting what had been a transform boundary into a convergent boundary.
Yeah, you still like that.
I do still like that.
Yeah. And then 46.
Same
Um,
story, it's just moved farther
mhm.
north.
Yeah, good. This is fun. Let's do a couple more. What else do I have? Well, here we go. So
Okay.
to involve the viewers just a touch more, and then I'll stall for Jeff for 30 seconds. This is the Idaho slab curtain. If you recall, viewers, Gene Humphreys says yes. Spencer Fuston says yes. Basil Tikoff says, I don't think that's an ocean slab at all. I think that's the kind of underplating of continental North America. Uh, but I'll let you go from here, Jeff. You like it can't be a coincidence that this boomerang is fitting nicely with what you have here. Am I putting words in your mouth
Right.
there?
No, no,
Please
no,
go.
that's
Yeah.
fine. So this was an attempt to take Spencer's tomography
Hmm.
and back it up to 52 million years ago when we think the slab broke off. So the blue dashed lines there are the modern boundaries of the slab in the subsurface as defined by Spencer's tomography.
Yes.
And then if we try to ask the question, if we undo the last 52 million years of subduction,
Hmm.
what would the geometry of the plate look like then? And so that's what the green hatchard. So if you take your cursor and put it right there and then just move it, that's the modern boundary, and then you just move it to there, move it to the green. That's the change that's taken place in the last 52 million years.
Yes.
So the things that were sort of intriguing to me were that if you look at the northernmost little bump there of the green hatchard zone, that right there, okay, the northern edge of that aligns with where the Farallon resurrection slab window would have been 52 million
Mm,
years ago. So that would be the northern edge of what we think broke off and rolled back.
mm.
And then right about at the eastern limit of that little bump where you are, this labeled break-off belt, if that's where the slab broke off, which makes sense, then that's where we today see this belt of 50, sort of 49 to 51 million year old
Mm.
plutons and volcanic rocks that I think are the consequence of the slab breaking off there,
Including the basalt of Summit Creek.
including the basalt of Summit Creek. Yes, that was actually the first. That was the first
It was.
member of this club because it was a class project, and all I knew it was an Eocene volcanic unit that hadn't been studied. So the class, the model was that we would go out in the field and collect samples, and then each student had two or three samples that she or he had to prep and chemically analyze and make a thin section and all that. So we probably had 45 samples or something because I probably had
Wow.
15 students. And so we had this big data set, and I wanted to give them something to compare it to see is it different. So I gave them all these crescent basalts, which are, part of Silesia. And I was expecting that they're going to say, well, this doesn't look like the crescent, but in
Right.
fact, it did.
Right.
And then we had to figure out, well, why does something that looks like oceanic basalt, why is it erupting, through the continent? And the answer we came up with is the slab broke off, and the same plumbing system that was feeding Silesia was now feeding a smaller volume eruption, but it was doing it underneath.
Okay, that's how we're going to finish.
Okay.
I think you've said this before. No, one more. This is coming right now. This is the wrap up. I think I heard this from you off camera a while back. Using all the geochem with all those class projects with your outstanding students at University of Puget Sound for the last 20 years. You not only had the age pattern of 52 down to 44, northeast to southwest, but all this geochemistry as well, without knowing any of the tomography that came
Right.
kind of more
Right.
recently.
No,
I
I mean
think,
that the tomography I got from watching Spencer on one of your shows a couple years ago, and I think I had read his paper, but I hadn't really processed it enough. So it was only when he started talking that I suddenly thought, here's a chance where petrology and tomography could actually tell the same story. So when I wrote the paper, I reached out to Spencer and said, do you think this is would you buy into this interpretation? And he helped me, come up with how many years of subduction is represented by the curtain. And that's where we got the 60 million years for the
Wow.
breakoff. But no, many serendipitous steps along the way, and watching that episode with Spencer was one of them.
Well, that is cool, and that is maybe where we're headed in general, possibly with a little bit more open communication between different areas of specialization. I heard a little frustration, I think, from Basil saying some of this tomography stuff appears to be just totally on its own engine and forgetting about some of these major structures that everybody's known about for the last 100 years doing some mapping. So you're kind of a surface guy. I don't know, is that the right way to say it? But you have
I'm
these.
above the moho.
You're above the moho.
I'm
You're
above the
damn
moho.
right. You're damn right. I'll say that about you. You've always said that about Jeff Tepper. He never goes below the moho. All right, great. That's perfect. Anything else to add on this? We might have you on again. I think maybe we'll do
No,
another video as
well,
well,
I just
Jeff.
say, it's an honor and a pleasure to be in class. This is the world's largest geology class, and I learn something every time. So
Very good.
thank you.
Okay. Thank you, Jeff. I'm gonna stop the
All
recording
right.
and we'll go back to talking just a little bit more.
Okay.
Thank you
Sounds
very
good.
much.
Thank you. Bye bye.
Bye bye.